Hello guys, welcome to the final episode of the EMG design series of videos. So in this video, we're going to see it's pretty much the practical side of the previous one, part 3 with 4. And since I'm going to be referring to that video a lot here, I highly recommend that you watch it before this one. So like I said in the previous video, we're going to deal a lot with electromagnetic interference. The previous demonstration that I made was in the ideal conditions, but right now we will get into a more realistic situation. So electromagnetic interference is caused mainly by inductive loads. So if you have any coil, transformer, relays, motors, all these kind of things. So basically any electrical device actually creates electromagnetic interference. So it's a huge problem when it comes to acquiring signals that are really small, like this, the biopotential signals. And since the device has to be really, really sensitive to be able to amplify those tiny things, the drawback is it's also going to amplify a lot of the noise. And the human body also, you know, acts like an antenna. And if you're in an electromagnetic field, it's going to have an influence on your body. So there's going to be a superposition of the surrounding electrical potentials on your own biopotential. So right here, I have my breadboard with the circuits, and I'm going to show you quickly the ideal situation. I'm just going to contract my muscle. Since I already showed that, I'm not going to spend too much time on this. So right now I turn on the device, and you can see that when I'm contracting my muscle, it's working. It's responsive. Everything is working fine. Now, like I said, pretty much any electrical equipment creates EMI. So even my laptop creates EMI. So if I bring it a little closer, you can see what's going on. I'm not contracting my muscle, I'm not doing anything. I just brought it closer to my computer. And of course, when I'm contracting my muscle, it's not working anymore because everything is diluted, everything is mixed up, and the whole thing is not working anymore. I've lost control. And if I bring it a little, just like that, it starts working again. And here, I also have a power extension cord. The same thing is happening. Now, I have not plugged anything on that, but you already see, even though the cable has this insulation, it's still able to create some noise. And here's a phone charger. And of course, in a phone charger, you have a transformer, a step down. So if I plug that in, you can see that it also, creates some disturbance. And if I throw it, I place it a little, further from it becomes, less strong. Now, if I do this, so you can see pretty much anything creates this, this electromagnetic field, this electromagnetic interference kind of situation. So And it's not really, I would say, realistic or practical to always make sure that you are always, you know, far from any other electronic equipment, in order for the device to work correctly. So to avoid doing that, it's a good thing to um, add some additional filtering for this kind of situation. And just like I did in my, I've shown in the previous video, I'll start with the notch filter. So here's my notch filter circuit, and I'm just gonna plug it into my device, and you're gonna see that the influence it's gonna have on it. So right here, as you can see, I have connected my notch filter, and I'm gonna turn on my device. Now, you can see that when I'm contracting my muscle, nothing is happening. And that's because, the notch filter creates a lot of attenuation on the differential signal. So I'm losing a lot of gain. And the gain is not strong enough anymore to amplify the difference in potential when I'm contracting my muscle. That's the drawback of it. But you can see that now I'm even, I'm getting the device really close to my computer and nothing is happening. The same thing. Okay, when I'm holding this thing, there's still a little bit of spikes going on, but it's not as bad as, okay, right now it's getting a little bad, but you know, the system can be a little, oh, actually, I have something that got disconnected. That's the reason why it's not, okay. So yeah, you can see it's it's not as bad as it used to be previously, but it's not working. When I was using the notch filter with my potentiometer, I amplified the initial gain by 11. So I multiplied the whole thing by 11, and the device was still not working. So that really shows you how strong of an attenuation we have with the notch filter. And right now, I am using the driven right leg method. And as you can see, when I'm contracting my muscle, I have something. And if I bring back the source of disturbance, you can see that, okay, we still have something, but at least, I mean, it's not as bad as when there is no filter at all. But at the same time, when I'm contracting my muscle with this, you can see that despite the noise, the device manages to work to a certain extent. You can clearly see the difference between when I'm contracting and when I'm not contracting. That's because I'm using the driven right leg. And if I put it away, it's like my system is just working normally. And if I amplify the gain, here I'm at maximum, just like what I did with the notch filter. But here you can see when I'm contracting my muscle, I have something. I have a result. I can go up to pretty much 1 volt. So that's the reason why the notch filter is in my opinion, or should I say objectively speaking, uh, the best solution when it comes to acquiring a differential signal. And like I said in the video, when I'm using the driven right leg method without the capacitors, I don't have good results. So I'm gonna show it right now by removing my capacitors. So right now I have removed the capacitors. So I only have the driven right leg with the resistor. And here I'm holding the thing. It's not as bad as if there was nothing, but still, it's still a little weird. You know, sometimes it works, sometimes it doesn't work. It's really not stable. Like right now, I'm contracting my muscle, but nothing is happening. And from a for a short period of time, it may work, and then 1 second after, it doesn't work. So the system is very, very unstable. And as you saw, it works definitely better when I add the capacitors. Another thing I wanted to say before the final demonstration is when you're using a breadboard like this, it does not help with EMI. You rather use a PCB. So this PCB is based on the circuit that was on the breadboard. Of course, when you're prototyping something, you always start with a breadboard. But if you don't have the best results on the breadboard, it's normal because it comes from, it's from the very nature of the breadboard. And I also wanted to show you something because, biopotentials are not mutually exclusive. So this is an EMG, but it can also, to a certain extent, work as an ECG. Now, it's not going to give the best signal because it's not designed to be that, but it can still, to a certain degree, acquire a heartbeat. So right now, I'm just going to place the electrodes on my chest so that you can see that it can also behave like an ECG. So yeah, as you can see, there is this spike that corresponds to my heartbeat. Right now, I have taped an electromagnet on my hand, and here I have some metallic objects. So I'm going to use the EMG to control them using the electromagnet. So right now, you can see the capacitor is discharging. So the blue one is the rectified signal and the red one is the reference voltage. I'm not plotting all the signals because it's not necessary. So I'm just going to stick with those two. So when I'm going to contract my muscle, I'll be able to control things. You can see right now I'm contracting and I'll stop. Cool. Contracting my muscle and I'll stop. Now, maintaining the contraction for so long is a little difficult, especially because when I'm in that position, I'm in in pronation. I can fully contract my muscle. I mean, it becomes significantly easier for me to contract when I'm like this, when my hand is facing upward, because this is the pronation state. So the biceps has the most power like that. But when I'm like this, I have to go really hard to be able to reach this kind of peak contraction, and it's difficult for me to stay like that. So let's do another test. This time, I'm gonna add some sound effects. The sound effect of NAN. As you saw in the thumbnail, I have this kind of NAN categories between manipulation or emission. Now let me know if you think that's closer to emission or manipulation. So let's go back. Thank you for watching the video. I hope you've learned a few things, maybe not with this one, but through the entire series of videos concerning the EMG design. And if you didn't watch all of them, no problem. You have them in the description. I hope that you've learned a few things, that if you were afraid of electronics, you've realized that it's not a big deal, that you can build whatever device you want for whatever purpose you want. This is a biomedical device, but I'm not taking it seriously. I'm just having fun with that, connecting it to my uh, anime fan side, you know, whether it's Dragon Quest or Hunter x Hunter, just I'm just having fun. But even though it's all fun and game, behind the scenes, it's real engineering. It's serious. You go through a lot of things like the design, the testing, multiple iterations. You're doing the trial and error kind of thing. You are, trying this, calculating whatever, having the simulation, the theoretical calculations, and then the experimentation, and even going through the whole process and making a PCB. And the next video is going to be about that. I'm going to share a few tips when it comes to PCB design. I'm not a pro, but I think I can share a few things with you regarding that. So yeah, thank you for watching the videos. Other videos, if you watch four of them, you're a real one. And if you didn't, you can still catch up, no problem. So see you next time. Oh, before that, I also want to apologize because, in some of my videos, the audio is not always good, especially when I'm recording on my phone. I'm getting started with that, the whole YouTube thing. So I apologize for that. And I hope that it does not discourage you to watch the videos or to understand what I'm trying to say. See you next time. Stay tuned. Bye.